Hi everybody. This is of Module 3 in Foundation Mathematics. We are going to see about the relations, types of relations, functions and types of functions with some examples. First, let us see about the definition of relation. If there are two sets x and y, then their Cartesian product denoted by x star y is defined as x star y equal to the set of all elements of the form a comma b, where a belongs to the set capital X and b belongs to the set capital Y. The elements of the product of x star y are also called the ordered pairs with the elements of x as the first entry and the elements of y as the second entry. For example, if there are two sets, capital X equal to small letter a, b, c, and capital Y equal to 1, 2, 3, 4, then the Cartesian product is a product between x is x star x equal to a comma b, and a comma c, b comma a, b comma b, b comma c comma a, c comma b, and c comma c. So this set of all ordered pairs is called the Cartesian product between the given set x into x, and there is a relationship between the set x. Okay. In another example, if x and y are two sets, x equal to a, b, c, and y equal to 1, 2, 3, 4, then we can form a set of all ordered pairs as x star y equal to a comma 1, b comma 2, c comma 3, or c comma 4, otherwise b comma 1, b comma 2, or c comma 1, c2, c3, c4. Okay. So there may be more than 12 to 20 combinations will be there. For our convenience, we can choose some of the set of all ordered pairs, or for all combinations we can go for. So this is the example for the Cartesian product between the two sets. Let x and y be two non-empty sets and let R be a relation between x to y, then the inverse relation is denoted by R power minus 1 is a relation from y to x defined by R power minus y equal to y comma x belongs to y star x, whose actual pair x comma y belongs to the relation set R. So for all small x belongs to capital X and small y belongs to capital Y, the ordered pair x comma y belongs to capital R if and only if the inverse y comma x belongs to R inverse. This is the definition of the inverse relation. Now let us see some types of relations. Identity relation, the first one. In an identity relation, every element of a set is related to itself only. For example, in a set capital A equal to A, the elements are A, comma B, comma C. The identity relation will be denoted always by capital I, which is equivalent to the set of all ordered pairs A, comma A, B, comma B, and C, comma C. For the condition for identity relation is capital I equal to the ordered pair A, comma A for all elements A belongs to the set capital A. Only for identity relation, it must satisfy for all the elements of the corresponding set. For the remaining relations, it is not necessary that for all the elements should satisfy for all the elements of the set. Only for the identity relation, it must satisfy the ordered pair of the corresponding number appeared in the original set capital A. Now, the second one is the inverse relation. Inverse relation is seen when a set has elements which are inverse pairs of another set. For example, if a set capital A equal to the ordered pair A comma B and ordered pair C comma D, then the inverse relation will be R power minus 1, or R inverse equal to just the reciprocal of A comma B is B comma A, and the reciprocal of C comma D is D comma C. So for an inverse relation, R inverse equal to B comma A, such that the ordered pair, original ordered pair A comma B belongs to the relation set R. In all those relations, we must remember that R is the relation is nothing but set of all ordered pairs of elements. So all the relation must always be in the form of Cartesian product or set of all ordered pairs. The third one is a reflexive relation. In a reflexive relation, every element maps to itself. For example, consider a set capital A equal to 1, 2. Now an example of a reflexive relation will be R equal to the combination 1, 1, 2, 2, 1, 2, and 2, 1. The general form of the reflexive relation is given by minus of A belongs to R. The reflexive of 1 is 1, reflexive of 2 is 2. But if you consider a pair 1, 2, the reflexive of 1, 2 is 2, 1. If the reflexive of 3, 4 is 4, 3. So in this way, you have to look at any two or for all combinations of the pairs. So in this relation set, we are having 1, 1 and its reflexive is 1, 1 and the reflexive of 1, 2 is 2, 1 appeared in the relation set R. Therefore, it satisfies the reflexive relation. The fourth one is the symmetric relation. In a symmetric relation, if A equal to B is true, then B equal to A is also true. In other words, a relation capital R is symmetric only if B, A belongs to R is true when A, B belongs to R. An example of the symmetric relation will be capital R equal to 1, 2 and 2, 1 for a set capital A equal to 1, 2. For a symmetric relation, if A is related to B implies B is related to A for every A, B belongs to A. Symmetric relation is nothing but it is just like a mirror image. So if you have seen the mirror, whatever it appears, okay, you can see it in the mirror. 1, 2, it's reflexive. Its symmetric relation is 2, 1. So in this set A equal to 1, 2, we are having 1, 2 and 2, 1 appears on R, capital R. Therefore, the symmetric relation is satisfied. And the fifth one is transitive relation. For a transitive relation, we have to consider two ordered pairs and we have to prove the third combination is also in the relation set. The condition is if x, y belongs to R and y, z belongs to R, then x, z belongs to capital R. For a transitive relation, if A is related to B and B is related to C, implies A must be related to C or A may be related to C. If it appears, we can say that it is a transitive relation. And it is satisfied. It is not necessary that for all the elements in the set A must satisfy the transitive relation. For some of the ordered pairs is satisfied the transitive relation, then we can call it as the condition is satisfied. So the condition is if A is related to B and B is related to C implies A is related to C. For every A, B, C belongs to capital A. For example, if A equal to in the set A 1, 2, 3, the relation set may be 1, 2, the ordered pair 1, 2 and the ordered pair 2, 3 implies the ordered pair 1, 3 if it belongs to capital R in the relation set, then the transitive condition is satisfied. The next definition is very important, equivalence relation. If a relation capital R satisfies reflexive, symmetric and transitive at the same time, then it is known as an equivalence relation. It is an important definition in the topic relation, equivalence relation. If it satisfies the first three conditions, reflexive, symmetric and transitive, it is called equivalence relation. The next topic is the domain, codomain and the range of a relation. Let A and B are two sets. In a domain, codomain and the range of a relation, if R be a relation from A to B, then domain of relation capital R is a set of all those elements small a belongs to capital A such that the ordered pair A, B belongs to capital R for some of the elements B belongs to capital B. Let R be a relation from A to B, then B is the codomain of R. Codomain or a range. The range of the relation R is a set of all those elements B belongs to capital B, such that the ordered pair A comma B belongs to capital R for some A belongs to A. In short, the domain of R equal to the set of all the single elements, the elements of the set, elements of the ordered pair, the first element of the ordered pair, and the range equal to the second element of the ordered pair. So range is always a subset of the codomain. So we can easily remember, and we can easily pick out the domain and codomain from an ordered pair, that the first elements of the ordered pairs are called domain and the second elements of the ordered pairs are called a range. And simple problems based on the concepts we have seen now. There is a relation capital R equal to the set of all ordered pair A comma B if A is related to B on capital A equal to 1, 2, 3, 4. Our question is R is reflexive and R is symmetric or is transitive? See here, I have drawn some capital R, the relation set R, whose ordered pairs of numbers are 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 4, 3, 3, and 4, 4. Our question is R is reflexive? The answer is yes. Because already I told you that if the elements of the set A are 1, 2, 3, 4, only for a reflexive, we have to consider all the elements of the capital A. For the first number 1, we must have 1, 1. And for the second number 2, 2. And for the third number 3, 3. Fourth number 4, 4 belongs to capital A. So for each element of capital A, we must have a set of all ordered pairs of the same number. If it appears in the relation set, then it is called reflexive. Second one, our question is R is symmetric? Answer no. It is not a symmetric relation, since in the relation set for 1, 2, 2, 1 must be appear, or 1, 3, 3, 1 must be appear. If 1, 4 means 4, 1 must be appear. 2, 2 means the 2, 2. Except the same number, if 2, 4, if 4, 2 appears, it is called symmetric. For a 3, 3, except the 3 and the 3, 4, 4. For the sets, the set of all ordered pairs 1, 2, 1, 3, 1, 4, and 2, 4. If its reverse numbers appeared in the set R, then we may call it as a symmetric relation. Otherwise, there is no symmetric relation, since 1, 2 for the ordered pair, we are not having 2, 1. So it is not a symmetric relation. So the second condition is not satisfied. And the third one is R is transitive. Yes, it is transitive, since 1, 2 and 2, 2. If it is A and B and B and C, if it belongs to R, the third combination, the ordered pair A, C, that is 1, 2 belongs to capital R. So for the transitive, the condition is if A, B belongs to R and B, C belongs to R, then if A, C belongs to capital R is satisfied, then it is called an transitive relation. And if any, and also we may consider for the second case, if R is symmetric, means for the set, for the ordered pair 2, 2, the 3, 3 and 4, 4, the reflexive of 2, 2 is 2, 2, the reflexive of 3, 3 is 3, 3. So the second condition is also satisfied. So we can tell that the symmetric is satisfied, and for the equivalence relation, we can say that the three basic conditions, reflexive, symmetric, and transitives, are satisfied. Therefore, we can call the set A as equivalence relation. A may be an equivalence relation. Example 2, or on capital A equal to 1, 2, 3, 4, such that A is not related to B if and only if A is not equal to B. This R is symmetric. If you look at the ordered pairs of elements for the relation set 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4, 4, 1, 4, 2, 4, 3. The question is R is symmetric? The condition is if A comma B belongs to R, then B comma A belongs to R. If it appears, the second condition appears, then we can call it a symmetric. For 1, 2, the 2, 1 appears. For 1, 3, the pair 3, comma 1 appears. Therefore, we can call it as a symmetric relation. And these are all the important topics under the relations. Now we will go to the next topic, functions. Function, let x and y be two non-empty sets. Let f be a relation between x to y. If f is called a partial function from capital X to capital Y denoted by f from capital X to y, if for every small x belongs to capital X, f of x is either a singleton or a empty set. So this is the definition for a function. For a function, we need two sets, capital X and Y, because we are going to correlate the two sets using the function f. If there exists a relationship between X and Y, then we may call it as a relation or a function. The another definition is if f is a partial function from capital X to Y such that for each small x belongs to capital X, f of x is a singleton, then f is called a function and is denoted by f from x to y. So here the domain of f is equivalent to x. The definition 2 is a function is a relation between a set of inputs and a set of permissible outputs with the property that each input is related to exactly one output. Let A and B be two non-empty sets mapping from A to B. It will be a function only when every element in set A has only one end, only one image in set B is called a function. For example, in the first figure, the number 1 is correlated to P, related to P, 2 is related to Q, and 3 is related to Q, but the third, okay, all the elements of the set X, if you consider 1, 2, 3 as your capital A and P, Q, R as your capital B, then all the elements of the set A are related to a sum of the numbers of set B. Then we can call it as a function. But in the second one, 1 is related to P, but 2 is related to the P, comma Q is related to the number 2, and 3 is related to capital R, right? So a function is a relation between a set of inputs and a set of permissible output with the property that each input is related to exactly one output. Each input, that word is very important, each input is related to only one output. But here 1 and 2 are okay related to the single variable P. So it is not permissible. That's why the second figure is not correct and it is not a function. Now we will go to the types of functions. The first definition is one-one function. Otherwise, we can call it as an injective function. If each element in the domain of a function has a distinct image in the codomain, then the function is said to be one-one function. That is the domain or the first set A and its codomain is the second set B. If each element in the domain of a function has a distinct or a single image in the another set is correlated as there is a relationship between first set and the second set with more than one elements in A but a particular element in a B, then it is called as a one-one function. Many-one function. If there are at least two elements in the domain whose images are same, the function is known as many-to-one. For example, if f from R to R is given by f of x equal to x squared plus 1 is a many-one function. The third one, onto function, otherwise called a surjective function. A function is called an onto function if each element in the codomain has at least one pre-image in the domain. Okay, we will see the examples in the next slides. Now, just go through all the definitions. Into function, if there exists at least one element in the codomain which is not an image of any element in the domain, then the function will be into function. A constant function. The function f from P to P is defined by small letter b equal to f of x equal to capital D, where a belongs to P, where D is a constant, belongs to P is a constant function. That is, the domain of f equal to P and the range of f is also equal to D. Bijective function. A function is bijective if for every y in the codomain there is exactly one x in the domain. Identity function. P equal to set of all real numbers. The function f from P to P defined by small and b equal to f of a equal to a. For each a belongs to P is called the identity function, where domain of f equal to P and the range of f is equal to P. Now, if you look at the diagram, first one is an example for one-to-one function or many-to-one function. For a one-to-one, all the elements of this set A are related to any one of the numbers or some of the numbers in the set B. Then we may call it as one-to-one function. Many-to-one means the 3 and 4 are related to the third element of the set B. Therefore, we can call it as many-to-one function. Not all elements of the codomain must be included in the range. That is important. In the B set, the last one is not correlated to any one of the element of B. Therefore, it is a simple function one-to-one and many-to-one. For a one-to-one means all the elements of the set A must be related to some of the elements of B, and if one or more elements in the set A are correlated to the set B, then we may call it as one-to-one and many-to-one. Second one, injective function. Not all elements of the codomain must be included in the range. It is a one-to-one only, because the elements of the set A are related to some of the elements of the set B. Therefore, we can call it as a one-to-one only or injective function. For a bijective, all the elements in the set A must be related to all the elements of the set B. All elements of the codomain must be included in the range. That is, if f of x equal to f of y, then x equal to y and f of capital A equal to capital letter B. Bijective is nothing but injective and subjective. So it is the combination of these two. And if you look at the diagram, all the elements in the set A are related to set B, then we can call it as a bijective function. And the next one is a surjective function, one-to-one or many-to-one. If it satisfies one-to-one and many-to-one, then we may call it as onto function or surjective function. All elements of the codomain must be included in the range. That is very important. The condition is f of capital A equal to B. Then we can call it as surjective condition. Many to one. Already I told you in the previous example, if more than one element of the set A is related to one element in the set B, then we can call it as many to one function. Into function means in some of the elements in the set B are not related to any one of the element in the set A. It is called into function. Constant function means if the set A contains variables and if set contains B contains numbers, then all the variables are related to only one particular number in the set B, then the corresponding relationship or the function is called a constant function. Identity function is very important for all the elements. Already I told you, for identity element, for every element of the set A must have a relationship with the same element of the set A. So if f from A to A is called the identity function. See here, both are A and A. The numbers in the set A are 1, 2, 3, 4, 5. So we can form a relation capital R equal to the set of all ordered pair 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Otherwise, if you have drawn like a mapping f from A to A, 1 must be related to 1, 2 must be related to 3, must be related to 3. 4 must be mapped into 4, 5 must be mapped into 5. So in this way, if you have compared, if it satisfies, we can call it as the identity function. The next one is very important, composite of two functions. A function composition is an operation that takes two functions f and g and produces a function h such that h of x equal to g of f of x. In this operation, the function g is applied to the result of applying the function f to x. That is, the function f from A to B and g from B to C are composed. to yield a function that maps x to capital X to g of f of x from A to C in Z is called a composition between two functions f and g. And this is an example for a composition of two functions. The upper diagram, f is a mapping from A to B. The elements of the sets A are 1, 2, 3, 4. Elements of the set B are 1, 2, 3, 4. F is mapped from 1 to 1, 2 to 3, 3 to 1, 4 to 2. Similarly, G is a mapping between the set B and the set C. The number B 1 to 1 is related to 2, 2 is related to 3, and 3 is mapped into 1, 4 is mapped into 2. And these two, if you combine these two, the resultant function is G composite F from A to C. The elements of the set A are 1, 2, 3, 4, and the resultant elements are also same 1, 2, 3, 4. But based on the above diagram, we have to come to a conclusion. That's why I have given different colors for the combinations for the functions. F from A to B, 1 to 1, but G from B to C is 1 to 2. So the final resultant function is G composite F is from 1 to 2. 1 to 2. Similarly, 2 to 3 and 3 to 1 will give us 2 to 1. Similarly, for the third function, f from A to B is f of 3 equal to 1, g of 3 equal to 1. Therefore, G composite f is from 3 to 2. And fourth one, 4 to 2, 2 to 3 will give us 4 to 3. The final composition function for two different functions, G composite f is from A to C. So from the above diagram, we can easily come to a conclusion that the composition between the two functions. Now, this is example 2 for the composite function. A composite function is created, one function is substituted into another function by problem solving method. But in the previous example, we have seen the mapping between the elements, but this is the algebraic method of solving the composite function. If f of x equal to 3x plus 2 and g of x equal to x plus 5, we have to find f of g of x and g of f of x. F of g of x means first we have to replace the inner function g of x as x plus 5. Then it will become f of x plus 5. We have to substitute the x plus 5 into the function 3x plus 2. So 3 into, instead of x, we have to replace it by x plus 5 plus 2. If you simplify, it will become 3x plus 15 plus 2 equal to 3x plus 17. Similarly, G composite f of x is nothing but g of f of x. So first replace the inner function f of x as the original function 3x plus 2, and now apply g of 3x plus 2 into the function x plus 5. So the x value here is 3x plus 2 plus 5 is nothing but 3x plus 7. Suppose if you are asked to verify whether G composite f of x is equivalent to f composite g of x, means that the final resultant are not same, because f composite g of x is 3x plus 17, but G composite f of x is 3x plus 7, both are not equal, the condition is not satisfied. So here one more example. Given f of x equal to x squared plus 6 and g of x equal to 2x minus 1, find f composite g of x and g composite f of x. For a first one, f composite g of x equal to, we can write it as f of g of x. Here, first replace g of x function as 2x minus 1. Now, it is in the form of f of x. So, in the f of x, replace it, the x value as 2x minus 1 the whole square plus 6. If you expand the a minus b the whole squared form, and if you add with the x, we can get 4x squared minus 4x plus 7. Similarly, G composite f of x equal to g of f of x value. Now, in the f of x function, replace x by x squared plus 6. And if you simplify, and this is the final resultant answer. And This is an extension of the two composite function. If there are three functions such as f of x, g of x, and h of x, then find the composition of these functions such as f composite, g composite, h of x for x equal to -1. Given f of x equal to x, g of x equal to 2x, and h of x equal to 3 of x, to find f composite, g composite, h of x, on the right hand side, first one f composite g of h of x. We can combine the g composite h of x as g of h of x. We have to simplify one by one. Replace the h of x function as 3x. Now it will become f composite g of 3 of x. Now substitute the 3x in g of x. G of x is nothing but 2x. So 2 into the x will become 3x. If you multiply, it will become 6x. So f of 6x is nothing but f of x is equal to x. So your answer is simply 6x. If x equal to -1, the condition given is if x equal to -1, then f composite g composite h of x equivalent to 6 into -1 equal to -6. That is the answer.